Join the conversation.
You're with Cape Talk.
And as always, one of the most popular segments of the show, consultant virologist at Addenbrooke Hospital in Cambridge, Dr. Chris Smith, also known as the Naked Scientist, joins us on air once more to answer a variety of your science-related questions. A very good morning to you, Chris. Are you there, Chris? Morning.
Do you know, I just made the most amazing rookie error and forgot to press the unmute button. Sorry about that. Good morning, Saskia. How are you?
Thought you were back in lockdown. I'm very happy to be speaking with you this morning. I need a little pick me up after last night. So we shall go straight to a caller. I do believe we have Zuki on the line. Good morning, Zuki. Welcome to Cape Talk. Please ask Dr. Smith your question.
Morning, Saskia, and morning, Dr. Chris. So I've got sensitive teeth, and I'm experiencing some additional tooth pain at the moment. And it made me wonder, why do we have nerves inside the tooth? Like, why can't they just be in the gums? And for that matter, why does the tooth even have like a blood supply? Why is it in the tooth and not just in the gums?
Thanks for that, Zuki. Dr. Smith?
Hello, Zuki. Teeth are living tissue, and you're quite right, they have a nerve supply and a blood supply. And inside the tooth, there is a pulp or a soft material, and the tooth is nourished by blood and therefore substances coming in via the blood. The nerves are very important because you need to know how much force you're applying when you're biting something. If you rely on just transmitted force through the tooth onto the jaw, then it's going to be spread out, it'll be much less accurate, and so you won't know how much force you're applying with each bit of your tooth onto whatever you're trying to eat. And so the nerve supply is incredibly important for being able to register when you're biting, how hard you're biting down on things. So we use that nerve supply all the time. We don't just use it also to gauge force, it also drives salivation, because when you're chewing things, you salivate and you lubricate food, you help it to make it easier to swallow and so on. That's also part of the reflex. The force being applied to teeth feeds back through the brainstem and triggers the salivary glands to squirt more saliva, because it assumes if you're biting down on something, you need salivation.
Yes.
Sensitive teeth, because the nerves are embedded in the tooth behind the enamel, which is the hardest substance in the human body. It's hydroxyapatite, which is a phosphate. When you add fluoride from toothpaste, this makes it even harder. But that can become worn down, especially along the gum line. When we scratch with a toothbrush and scrape, and if you're not careful not to apply too much force, you can actually gouge a hole in your enamel layer. It will also be broken down by microbes that are carriogenic. So they form dental caries, the microbes, by converting sugars in the mouth into acids. If you thin the enamel, you bring the outside world that bit closer to the more sensitive living inner part of the tooth where those nerves are, and hence you develop a sensitive tooth sensation. And things like extremes of cold especially, but also heat, can trigger a painful sensation. You can treat this, and there are various toothpastes that help to remineralize the surface of the tooth a bit, and that helps to build up a barrier. And also there are ways of desensitizing the nerves a bit with other things as well. So you can actually treat it. The best thing, though, is not to have that happen in the first place. So when you brush regularly, that's a good thing, but don't brush too hard. Toothpaste is really very harsh. It's quite a strong erosive agent. In fact, I think there's a apocryphal story of someone escaping from prison with dental floss and toothpaste by filing through the bars of their cell, because it's really quite a harsh chemical. So use it carefully.
Then, Chris, what about people who have had caps or implants? I mean, how does that then affect how the entire ecosystem of the mouth works?
Well, when you put a replacement for a tooth in, you mount a peg into the jaw, and this is then acts as a foundation for the tooth to be screwed onto that peg. This still transmits force onto the jaw, and bone is very richly innervated. That's why when you break a bone, it hurts, and so you don't completely lose all sensation of force being applied through your jaw. You just don't have the same precision that you would get with an individual tooth telling you how hard that you're squeezing down on your food. And most people adapt, and you don't have this done to all your teeth, so you're not going to immediately lose all of your mouth sensation.
We're talking to Dr. Chris Smith, or the Naked Scientist. I do believe we have another caller on air. Is it Foloso?
Hello.
Hi,
Thanks for
Foloso.
taking my call.
Yes.
I have a question about sounds. Are there any sounds that are unaudible, that are in the air that we can hear, as much as there's light that we can see?
So you're saying that in the same way that when we look at a rainbow, we can see the spectrum of the rainbow, but there are other colours of light that are invisible to us. For instance, X-rays and gamma rays and infrared. They're different wavelengths of light that are there, but we can't see them. Is there a sound equivalent? Well, the answer is absolutely yes. Humans hear down to a few tens of hertz, and once we get below that, we find it much more difficult to discern audibly with our ears. Our ears just can't pick up those vibrations. At the other end of the spectrum, once you go beyond about 15,000 cycles a second or hertz, our ears are not set up to hear those unless you're very, very small and very young. You can hear up to about 20,000 hertz, but this diminishes with age. Once you get beyond that threshold, though, we can't hear those sounds, but they're certainly there. In the case of lower frequencies, there is what we call infrasound, and these very low frequency vibrations are in the environment, and we're not nonetheless insensitive to them, though. Because they're quite long wavelength waves, they will actually recruit vibration sensors all over the body, in your bones, but also especially in your abdomen. And this might be where part of the terminology of having a gut instinct and feeling uneasy comes from. If you go to places where there's a lot of infrasound, old buildings, certain places where the environment tends to resonate with these sorts of sounds, people say they feel a bit creepy. And it may well be that you're recruiting or activating vibration sensors across your body, and that uneasiness is these being turned on by this low frequency sound that you can't hear, but you're effectively hearing it by feeling it. At the opposite end of the spectrum, although we can't hear these very high frequencies, they are certainly there, and many animals can hear them. Bats classically use them as part of their sonar, because by sending out very high frequencies, they have a short wavelength, and this means they get very good resolution of the space in front of them. They can see tiny insects because they distort or deform the echoes that they're getting back of those sound waves they're emitting, and that's how they pick out something like even a gnat flying around in front of them. They can go and find it and eat it, and they avoid running into things. And also other animals also produce these sounds. Mice classically scream at very loud volumes in the ultrasound regime. We can't hear it, but they certainly can, and they almost certainly use it as a means of communication, as well as producing audible frequencies we can pick up on. So yes, sound is just as rich in many respects as the light spectrum that we can and can't see.
Fascinating. We have a voice note from MFE. Can we play that one for Dr. Chris?
Greetings. Question for Dr. Chris. With regards to sodium, what is the impact of it on our heart health? And especially when I look at when you're testing for BP, they said if the bottom number is high, that means you have fluid retention, which means translates to the high sodium level in the body. And we always thought that sodium only comes from salt, but I've recently found out that sodium also is available on baked goodies that are baked with baking powder, which is a form of sodium. And you basically have nowhere to run, because you get sodium on cooked food, which is salted. You get sodium on baked goods, which is with baking powder. So what is the impact? Am I suddenly intolerant to sodium, or what is happening in my body that it is now starting to reject the sodium, or is starting to see a high level of sodium?
Great question.
Sodium is one of the so-called cations in our body. And you have a lot of sodium in your body, but most of it is not in your cells. Most of it is in your bloodstream. Cells push sodium out and they pull potassium in. And this is actually how they create an electrical gradient across our cells in order to make things like nerves and muscles work. So sodium is therefore mostly extracellular. And because sodium is very osmotically active, in other words, it pulls a lot of water with it, the more sodium you've got in your body, the more water you're going to hang on to. So you're quite right to connect sodium to blood pressure, because if you have a lot of sodium in your body, you will retain more water. And there is a very famous study done about 20 years ago called the InterSalt study, where they looked at the relationship between how much sodium a person takes into their body and the change in blood pressure over their life course. And people with a higher sodium intake tend to have a higher blood pressure, and the longer they've had that sodium intake, the higher the blood pressure tends to become up to a point. So there is an association between dietary sodium and long-term change and increase in blood pressure and hypertension risk. But when you do have high blood pressure, one way it's controlled with drugs is by causing the body to lose sodium. These drugs persuade the kidney to throw away more sodium than it otherwise would. And if the sodium goes into the urine, it pulls water with it, which reduces the total volume of fluid in the body. And that's where your point you were alluding to about fluid retention. If you lose fluid from the body, part of the rationale for how this controls blood pressure is that when fluid returns as in the form of blood into the heart, it fills the heart very hard, stretches the muscle, and the heart therefore pumps more blood out. If the heart is pumping a bigger volume of blood out into your arteries, the arteries are stretched more, therefore the blood pressure is higher. If you reduce that so-called preload, so you return a bit less blood to the heart because there's less blood in the blood vessels, therefore you will pump out a bit less blood, therefore you will stretch your arteries a bit less, and the pressure is a bit lower. So that's the rationale for how some forms of antihypertensive actually work.
And I mean, does this change over time? I mean, all of a sudden, as we get older, are we able to tolerate sodium less?
Well, as we get older, of course, everything else begins to stiffen up. And so blood vessels become less elastic with time. They lose their elasticity. They also gain more calcification and stiffness and rigidity. So even though you might be pumping the same amount of fluid out, the blood vessels are less compliant. They can't stretch as much. And so therefore the pressure is higher. So you also tend to get an elevation in pressure with age because of arterial stiffening, not just because of volume effects from sodium. And part of the increase in sodium load and water in the body can be a response to the aging of your heart muscle. Because as your heart gets older and less efficient at pumping, what can happen is that the body responds because the kidney says, well, I don't seem to be getting the blood flow that I'm used to. So therefore, it must be because I've lost a lot of blood. So what I'll do is I will kick in a mechanism to absorb more sodium and therefore hang on to more water to increase the volume of blood. And that will put blood pressure up, and that will help me get the blood flow I need. And then what you do is overload the system with too much water, because what it does is it forces your heart to pump out more water, more blood than it otherwise would, putting the pressure up to perfuse your kidney better. But that does translate into higher blood pressure. And that's where actually reducing the excess fluid does help to reduce pressure again.
We're taking your calls and questions for The Naked Scientist. Let's get to Promise's voice note, please.
Good morning. Question for Dr. Chris. I'd like to find out, Dr. Chris, what controls emotions and mental state of a person? The reason I'm asking is that, we have people who take soccer very seriously, so serious in such a way like losing feels like somebody has died, feels like you're mourning somebody's death, But then when I compare that to me, like literally the only thing that would set me back is somebody's death. But anything else, I can worry for that moment, but I continue forward because life moves on. So why are other people so emotional, drag whatever that is happening, even if it's out of their control, but some others are able to move on quickly like me?
Great question, Kay.
The Liverpool manager, Bill Shankly, famously said, "Some people believe that football is a matter of life and death. I am very disappointed with that attitude," he said. "I can assure you it is much more important than that." So the bottom line is that some people take things incredibly seriously, and some people tend to get very emotionally invested in them. And they basically are using a mechanism in their brain where when we regard something as a high priority, we we put enormous effort into achieving that, or righting a wrong, dealing with whatever it is that we've got locked onto that is a problem. And from an evolutionary point of view, that's a really good thing, isn't it? Because if that happens to be something like I need to get a drink, or I need to get food, or I need to save someone's life, you need to be able to focus very hard and be very emotionally attached to something in order to make it happen. It's how successful people become successful. You generally find people who are successful in business, for example, they have a goal, they're very driven, they're very goal orientated. So this is not a bad thing to have a target and to be extremely keen on achieving it. But in some people's cases, like all things, there are some people who will go a bit too far. And there are some instances with certain things, training, for example. Some people go a bit too far, and instead of doing themselves good through training, they train too much and they pick up injuries. It's human nature. And there are some people who are very good at sitting in that middle ground. There are some people who will go that little bit too far. But that's because we are, as a population, a huge diverse mixture of different brains, brain structures, and different ways that we tend to work, and you will therefore get people who sit at the extremes. While the vast majority are in that normal distribution, what we would call normal, there are always going to be some extremes who go that little bit too far.
We've got a note in here from Vernon wanting to know, saying humans have some of its population that have a condition termed color blindness. Green and red can't be distinguished. Do other primates or maybe some other mammals also have this condition amongst its population?
I don't know the answer to that, but it's an excellent question. And I would suspect that the answer is yes. I mean, we do know, for example, that some animals naturally see fewer colours than we do, but whether they have polymorphisms, genetic reasons why they can't see certain colours as a subgroup within a population, I don't know the answer to that. And I'm going to take that away as homework and find out. But I would instinctively say almost certainly. Now, the reason that we have colour blindness in humans is because we have cones. These are the light-sensitive cells at the back of the eye, the photoreceptors, that are sensitive to different wavelengths of light. And there are ones which are sensitive to ones at the red end of the spectrum, ones that are sensitive to things in the middle, the green part of the spectrum, and ones that are sensitive at the blue end of the spectrum. And these all overlap in terms of their sensitivities, but some people have a form of the gene that makes the chemical in those cells that's sensitive to light not make one of the particular chemicals or not produce enough of it. And so this has the effect where trying to discern a difference between things at the red and green end of the spectrum can be more problematic for them. And so those cells fire off equally when they see different colours, instead of firing off more when they see one colour than the other, which is how we discern colour. And so when a person who has colour blindness sees one colour or the other, they actually see the same colour, whereas a person who doesn't have colour blindness would say, well, I can see two completely different colours. Now, some animals are naturally like that. Dogs, for example, don't have that same colour distinction. Monkeys have additional colours in their eyes, so they're much better at seeing certain ranges of colour than we can. And the argument goes that they probably use this to discern whether a piece of fruit is ripe or not. And it looks the same colour to us, but they can see that it's clearly a different colour. I strongly suspect there are going to be animals out there that, just as we have gene changes that mean that some of us can't see certain colours and tell them apart, I suspect there are going to be animals that are very, very similar, but I will come back with some concrete evidence and examples next time. It's a brilliant question.
I think we've got time for one more. Can we do Promises voice note, please?
Good morning. Question for the naked scientist. How come the skin is able to repair itself? Bones are able to repair themselves. Teeth are able to repair themselves. And the liver is able to regenerate. How come the heart is not able to repair itself, or the kidneys, or even the lungs?
There are some tissues that have a really good regenerative capacity. There are others, the brain is the classic one, which repair very poorly if injured. If you do damage to the central nervous system through, say, trauma, a head injury, or stroke, nerve cells there do not regenerate. If you damage the heart with a heart attack, you do not get regeneration to any appreciable degree. You get healing, but you form a scar and fibrous tissue in the heart. You don't produce many, if any, new heart cells. Now, we don't know exactly why this is, but we do know that humans are different to other animals. There are some animals which, if you do damage to their heart, they will fix it. There are fish, for example, if you make a lesion in the heart of a fish, it will grow a new one. There are animals where if you chop its optic nerve, it'll grow a new one. People have done experiments on frogs and newts, and goldfish do the same thing. If you chop their optic nerve, you can even take the eye out and put it back in again, and the optic nerve will regrow. In that instance, it's because there are stem cells there which know, in inverted commas, that trauma has happened. We need to make some kind of repair, and those stem cells then produce a new population of cells to reconnect from one thing to another or repopulate the tissue that's been damaged. Livers restore themselves by doing that. Kidneys can't do that, as you say. So some tissues can, some tissues can't. The skin does. It probably comes down to what evolution has selected for. There are situations where you're going to injure things quite often, like bones and like skin, so it's evolutionarily beneficial to be able to fix them. Have a massive stroke, probably someone will have turned you into lunch and eaten you before the years have gone by that it's going to take to repair you. Have a massive heart attack, again, you're turned into someone's dinner before you have a chance for your heart to put itself back together. Tiny little fish, on the other hand, can happen very quickly, and therefore it's been selected for in evolutionary terms because it's a simpler system to put itself right.
Dr. Chris Smith, thank you so much. That's where we've got to end it. Of course, The Naked Scientist joins Clarence on Views and News every single Friday, and you're welcome to send in your questions for next week.